You have two different equations you're going to need to use. You're going to have to calculate the energy change for the water cooling down and the energy change for freezing the water, and you're going to add those two together to get the total energy change. Okay? For the water cooling, you need to know the equation is Q equals mass times specific heat times change in temperature. Okay? So we need to know the mass. The mass in the problem is 120 grams. Is that right? Specific heat for liquid water. Now, if you look on the handout that I gave you and look on the graph on the very first page, all this is kind of explained in one graph. All right? Where we have heating or cooling water down here, that's just this region right here. Okay? In the example problem in the homework or the handout, this is referred to as region 3. Okay? So this is heating or cooling water, and the equation that fits for heating and cooling water is right here. Okay? And then we've got a phase change where we're freezing the water. Okay? And that equation is shown right here. All right? So for the cooling of the water, it's 120 grams, the mass. Specific heat, this is a number you need to memorize, 4.18 joules per gram per degree C. Okay? Change in temperature we're going to have to calculate. Change in temperature is always temperature final minus temperature initial. Okay? The final temperature, if we're getting it down to the freezing point, temperature final is going to be 00 degrees C, and temperature initial is going to be 25.0 degrees C. So the change in temperature is 0.0 degrees C minus 25.0 degrees C. You should be adding these vertically to make sure you're keeping up with significant digits. But if you do it correctly, you should find your change in temperature is negative 25.0 degrees C. Now we're ready to plug everything into this because we now have all three values to find Q for the cooling part of things. So here is Q equals the mass of 120.0 grams times the specific heat, 4.18 joules per gram per degree C, times the change in temperature is negative 25 degrees C, negative 25.0 degrees C. And we do the math, and I got negative 12540 joules. I need to cancel units here. Grams are going to cancel, degrees C are going to cancel. That's how we have joules left. Okay? We need to round that to the correct number of significant digits. I've got 4 significant digits in this measured number, 3 significant digits in this calculated number, 3 significant digits in this calculated number. So in the final answer, we want to have the same number of digits as the measured or calculated number with least digits. That would be 3 for both these. 1, 2, 3 significant digits, and underline the 2 insignificant digits and round off. Now, since I'm rounding off a digit in the ones place, it's required that you write your answer in scientific notation. Okay? You might have chosen to wait to the very end to convert to kilojoules, or you could have done it in each stage. Okay? I'm going to wait till the end to convert to kilojoules. All right? Doesn't really matter. You'll get the same answer. But whenever you're rounding off, if you have to round off a number in the ones place, you need to make sure you do so by writing your answer in scientific notation. We're moving the decimal place 1, 2, 3, 4 places to the left. So our answer is going to be a negative 1.25 times 10 to the 4th joules. Okay, at least that part of the answer. That's just the first part of the problem. Okay, now the next thing is when we're freezing the water. So this same equation is used for any time you're changing the temperature without changing state. Okay, this equation is used for changing temp, but not changing state. Okay, that's when that equation is used. If we're going to be freezing, that's changing the state. For that, we need Q equals mass times the change in enthalpy. Okay, so this is used whenever you're changing state, physical state. All right, so we already know the mass. It didn't change. It's the same amount of water we're freezing. We know the delta H. The delta H are the change in enthalpy for fusion. There's 2 different delta H's and 3 different specific heats for water. In fact, there's 2 different delta H's and 3 different specific heats for anything. Okay? Because the physical state matters, and whether you're changing from one physical state to another physical state, which one of those changes you're making matter. All right? So for water, the value of delta H that you're going to need for fusion, and that's also true for melting. If you're freezing water or melting water, this same delta H number applies, and that's 334 joules per gram. Now, in this case, we are freezing, which means energy has to be removed, which means that delta H has to be negative. Okay? So this value is going to be negative. All right? Does that make sense to everybody? Because you're removing energy, delta H in this case is going to be negative. If you're adding energy, delta H is going to be positive. All right? Now you might figure out the negative goes somewhere else at a different time, but you need to know if you're moving energy, your Q value is going to end up being negative. Has to be. All right? So we notice this Q value was negative. If we're removing heat energy to freeze something, then the delta H, or the Q, actually ends up having to be negative. Whether you figure it out belongs here or just the final Q, you say, well, that has to be negative, and you change it. You know, you got to know removing energy required. I mean, freezing something means you're removing energy from that material. All right, so we need this equation. The mass we already know, 120.0 grams. The delta H is 334 joules per gram. Grams are going to cancel. We're going to do the math, and we get negative 4080 joules. Again, we have to consider significant digits. This calculated number here has the least digits. We'll have the same number of digits in our final answer, 1, 2, 3. Underline those and round it off to a negative 4.01 times 10 to the 4th joules. Okay? All right, so we've got the 2 parts. Now we're going to have to add them together. Okay, we have to add the cooling change in energy to the freezing change in energy to get the total change in energy. And so we're going to find this number here, negative 1.25 times 10 to the 4th joules, plus negative 4.01 times 10 to the 4th joules. And you need to be careful about how you do your significant digits. In this case, I gave you a problem where the exponents were the same. Kind of made it easier on you. But if I have two different exponents, you've got to figure out what the significant digits are when you're adding and subtracting. That's a little bit trickier. Okay. One way to do this is to put the zeros back on there so we can get it out of scientific notation. But remember, those zeros are insignificant. So it would work like this. I would say negative 1, 2, 5, 0, 0, and I'll underline the insignificant digits here to remind myself those are insignificant. If you don't remind yourself by putting that line under there, those are insignificant, you'll end up getting the answer wrong, or the right number of the digits wrong. Okay? And we're going to add to that, because it's addition, negative 40100 joules, and those two zeros there on the end are also insignificant. So we add those together, and we get negative 52600 joules, and those two zeros are insignificant. Okay? When we round that off, then we get negative 5.26 times 10 to the fourth power joules. Okay? So negative 5.26 times 10 to the fourth joules. Now, in this case, and only in this case, because the exponents on the 10 are the same, you could add those two numbers vertically. But it only works. You got to be careful about this one. So negative 1.25 times 10 to the fourth joules, and negative 4.01 times 10 to the fourth joules. Okay? It wouldn't work if that was a 10 to the fifth. Couldn't do that. Okay? But if you did it this way, you get negative 5.26 times 10 to the fourth joules. Okay? Either way, you get that same answer. All right? Now, the question, though, asks you to find your answer in kilojoules. So we still have to convert the joules into kilojoules. And you should know there are 1,000 joules in 1 kilojoule. All right? Using that, we can build a conversion unit, taking this number, negative 5.26 times 10 to the fourth joules. Put it over 1. Here's our equality statement to justify building this conversion unit. I want to match units on the bottom here. 1,000 joules go on the bottom, and 1 kilojoules go on the top. Joules cancel. Do the math. Negative 52.6 kilojoules. There's our final answer. Any questions about how we got the answer? It's better to round at the end. If you wait to the end to round, the difficulty is when you have multiple types of calculations using different types of rounding, figuring out at the end of a really complex problem, figuring out the significant digits at the end of a complex problem like that is really complex. So I've been having you round at every step. If you choose not to round at every step, and I'm giving points for rounding at every step, then I have to count off all the points for rounding incorrectly for every step. That makes sense? So let's say I rounded here and so forth. If you only rounded at the very end and you're wrong, then I don't just count off the points that are wrong here, but the points up here that are wrong as well.
What if you get it right, though?
Then you get it right. You don't lose any points. Okay? But, you got to know how my point systems are set up for people to do it the way that I teach it, right? So, the thing is, you might lose double points because I'm expecting to see rounding in two places. You're only showing it in one place. If it's wrong at the end, you lose double points. Does that make sense? All right, just so we're clear. Worth 75 points. So, this equation here, you have to show your equations, always have had to show your equations. That's worth 5 points. Okay, the math, where you calculate to the energy change for the first part of the problem. That part's worth 26 points. The second equation here that you have to use, that's worth 4 points. The math for finding out the answer to this part of the problem with all the units of measurement and cancellations of units of measurement, equal signs, time signs, that's worth 15 points. Okay? Adding the number of joules, the value of the joules together with all the units of measurement and operators and stuff and underlining and arrows, that's worth 7 points. Since you have to convert to kilojoules somewhere, you have to have this equality statement written somewhere, and that's worth 5 points. Correctly converting to kilojoules, whether you do it at the very end like I did or in steps with all the cancellations and operators and units of measurement and stuff, is worth 13 points for a total of 75 points for everything. Okay, please give me your attention. Now, again, it's important that you know when delta H and delta T are supposed to be negative. Okay, now delta T should come out to be negative when you do the delta T equals temperature final minus temperature initial calculation. But then if it doesn't, you need to be smart to figure it out. So that's sometimes called a reasonableness test. If you know that you're cooling down something, so the temperature is going down, and your temperature did not come out to be a negative, your change in temperature didn't come out to be negative, the reasonableness test would tell you that's not reasonable. Because if I'm removing heat from it, if I'm cooling it down, my temperature should be my change in temperature should be negative. That makes sense? The same with delta H. If I'm removing heat to either condense something as we have at this part of the graph or freeze something as we have in this part of this graph, then the delta H has to be negative. Now, it's not automatically going to come out that way for you in a calculation because we don't have a calculation for delta H at this level. All right? So you just have to know. If I'm boiling something, that's this range here, delta H is positive. If I'm condensing something, delta H is negative. If I'm melting something in this range, then the delta H is going to be positive. If I'm freezing something, delta H is going to be negative. Now, the question was asked, why is this range so much shorter than this range? Okay? We're looking at the amount of heat energy added, right? The x-axis is an amount of energy. The delta H for freezing and melting water is 334 joules per gram. That's not a whole lot of delta H, right? Okay, so you don't need as much energy to get that phase change to take place. But for turning it into steam, we've got a delta H that's many times that amount. Okay, 2,260 joules per gram. And so in order to get that phase change to be complete, you had to have added a lot more energy. That makes sense? And that's why the steepness of these slopes are a little bit different too. Okay, now this is a generalized graph. The actual steepness of the slope I have here is sort of estimated. All right, so but it gives you some relative ideas about things like that. Okay, now, so you need to know delta H is negative. Also, you also need to know that if you're cooling something down, Q is going to be negative, right? Because you're removing energy to make that happen. If you're freezing something, you're removing energy, so Q should be negative. Got it? If you're boiling something, you're adding energy, Q should be positive. If you're heating something up, Q should be positive because you're heating it up. All right? So that's also a reasonableness test for a lot of calculations here. All right? Now this is all based on some theories that a guy named Carnot came up with a long, long time ago when there were only steam engines. And so what he was trying to do was to figure out how do we make steam engines more efficient. And what he did was create this theoretical idea of the perfect steam engine, where there's no loss of energy due to heat loss to the atmosphere or friction. It's just, you get all the energy out that we put in. And so that theoretical construct, that theoretical idea is called the Carnot engine. Okay? And since he came up with this at a time when the only energy we really knew about was heat, enthalpy has a capital H as its symbol. At one time it would have meant just heat. But now we know there's more than one kind of energy, and we use H. We still use H. It's just been carried down to us. Okay. So even though H is not, isn't the same letter as enthalpy, that's where it comes from. All right. And it's all based on this idea that when we say a perfect engine, then there's no heat loss to the atmosphere. All right. The assumption is in a Carnot engine that all the energy stored in the coal is transferred directly to the water, which is turned into steam. There's no loss. That can't happen. That's impossible. But it's a theoretical assumption to compare it against. So that when we find out just how efficient the engine is, we compare that to the perfect engine to get a percentage, or something like a percentage, or fraction of perfection. That makes sense? Okay? All right. Now, you need to know that energy cannot be calculated directly. Energy cannot be measured directly. Energy has to be measured indirectly. So energy cannot be measured directly. All right? What we have to do is to measure an exchange of energy through work to figure out, or through some other means, to figure out what the energy was. Okay? It's also true that enthalpy, which is a type of energy, stored energy, we often think of it in high school as enthalpy being stored energy. It's actually not quite stored energy. There's more to it than that. But at the high school entry-level chemistry level, we can assume, when we do all these assumptions where it's like simplifying to the point of absurdity. You've heard me say that before. That's kind of what we're doing here. We're assuming for this rudimentary beginning understanding of what enthalpy is as being stored energy. Okay? And since energy can't be measured directly, enthalpy cannot be measured directly either. It has to be measured through some change. All right? And that's what a lot of our calculations are all about. Now, in order to figure out what these changes are, we have to understand some more theoretical ideas. And that is that if we're looking at how things are changing, we've got to figure out, well, where are they changing from and to. So in our graph from your homework, we had heat energy added to water. Okay, that's what heat energy being added was on the x-axis. Sometimes you see this as time on the x-axis, but what's happening is heat energy is added consistently over time. So essentially it's adding heat energy even though it may be time on the x-axis. Well, where did that heat energy come from? If this is our system, and it was for these calculations, then the heat energy came from somewhere outside that system, and that would be the surroundings. So the theoretical idea is that we have something called the system, and that's the area where we're measuring or trying to find out about a change either in temperature or energy or something. And energy in the system is constant. It doesn't change unless it goes somewhere or it comes from somewhere, and where it goes or comes from is called the surroundings. Okay? It goes from or comes from, goes to or comes from the surroundings. And all together, the system and surroundings make up our universe. in order to figure out energy exchange, we have to make some assumptions, and there may be good assumptions, may be poor assumptions, or you may calibrate for the poor assumption. We have to assume that we're looking at a limited part of the universe, because we can't look at the whole universe. No way we can do that. We can only look at a limited part of the universe. So generally what we do is we try to isolate a small part of the universe. We try to create a mini-universe by somehow isolating or insulating that part of the universe from the rest of the universe. Okay? Creating our own little mini-universe to study. And here's how we might think about that. Let's say we have a container. Maybe it's a beaker or a cup. And we're going to put in that container some water. So we've got water in our container here. And just for the sake of this example, we're going to say this water is about 300 grams. That's about the size of a medium-sized, or at least a medium-sized beaker for us in a high school chemistry lab. And we're going to start with a temperature of this water of 10 degrees C. Okay? Now, because we want to keep this as our mini-universe here, all right, in order for that to work, this has to be perfectly insulated, which means to say that no energy, no heat, no temperature change can occur from this, what's inside here, to the outside. Okay? Well, you cannot perfectly insulate any container. It's not possible. We're going to assume that for our exploration here, but in fact, if we were actually doing this and doing a really good job with the calculations, we would actually calibrate this container for the heat energy that's lost or gained to the surroundings. Okay? So we determine how much heat energy is lost or gained and include that in our calculations for heat exchange in this system. Okay? But this is our mini-universe. Or it's actually going to become our mini-surroundings here in a minute. I'll show you what I mean by that. So we're assuming, for the purpose of our theoretical discussion here, that this is a perfectly insulated container. All right? Into this perfectly insulated container, let's add ourselves a chunk of iron. Okay? And for the sake of this theoretical problem, we have a perfectly insulated mini-universe here, that the iron's mass is 50 grams and with a starting temperature of 45.0 degrees C. All right? Now, what we're going to do with that iron is we're going to stick it inside our mini-universe. All right? So, here's the first question I have for you. Now, this is a question that you can answer from practical experience. You don't need to have any theoretical understanding or fancy chemistry knowledge or whatever to figure this out, because this is something that's pretty common knowledge. People kind of understand this instinctively. What happens to the temperature? What? Which rises? The iron or the water? The water temperature rises, they're saying. Okay? What happens to the temperature of the iron? It goes down. Pretty practical. You understand? You kind of know what's happening, right? Yeah, okay. All right. So, what's going to happen here is that the water temperature you're expecting to go up, and the iron temperature, you're expecting to go down. And when does it stop going up and down? When they're the same temperature or you reach equilibrium. All right, so that keeps happening until both of them have the same final temperature. Okay? Same final temperature. Now that's going to be important in some of these calculations. Do you understand theoretically where we're going? All right, now if you keep the theory in mind as you do the math, then whether your answers are reasonable or not makes some sense. Okay? As we apply the reasonableness test, this is the idea you want to try to remember. Okay? And in the ice cream lab, it's part of what you want to remember. Okay? At least in the preparation for the ice cream lab. The math you have to do to be successfully, or the math you have to be able to complete successfully in order to be allowed to eat the ice cream you're going to make. All right? All right. It's an important thing that you remember that the energy content of the universe never changes. Okay? You cannot add to our universe any energy, and you cannot take any energy out of our universe. Okay? So Q for the whole universe is constant. Okay? What can change is Q in the system or surroundings. If Q increases in the system, because the universe Q is constant, the energy in the universe is constant, if the energy in the system goes up, surroundings have to go down. That makes sense? Because you're moving energy from the surroundings to the system. On the other hand, if the system's energy goes down, that energy has to go to the surroundings, such that the universe's energy content is constant. All right, so let's consider a little mini isolated universe then, okay? This one right here. I want to find out what that final temperature is going to be. And you already have the math equations to do it. It doesn't matter whether it's water or iron or anything. The equations for changing temperature are the same. Q equals M times specific heat times change in temperature. Okay? Those equations don't change. So, we said the water temperature is going to go up, yes? Therefore, its Q, which is the amount of energy it's absorbing, is going to be positive or negative? Positive. So we're going to have a positive Q, and if the equation is mass times specific heat times change in temperature, okay? And we said the iron is going to, its temperature is going to go up or down?
Down.
It's going to go down. So is its Q going to be positive or negative? Negative. And it's still the equation mass, specific heat, change in temperature.
So in this scenario, the water will be the surroundings and Q will be the system?
Alright, so the question is, in this scenario, will water be the surroundings and iron be the system? Is that what you're saying?
Mm-hmm.
Okay, what do you guys think? Is our analysis correct, or would you disagree?
I agree.
I'm confused about our mini universe thing that we got going on.
I think the iron in the water is the system.
Okay.
The surroundings is the air around it.
All right, but we're assuming a perfectly insulated container where we're creating our own little mini universe here. So this is indeed the universe in our theoretical construct. All right, so one person's saying iron's the system, water's the surroundings. Another person's saying it could be either one.
Because you can think of how
The container is the universe.
Okay, got another person saying the container's the universe, and everything inside, iron and water all together, makes up system and surroundings. Which one's the system?
They're each other.
She said they could be interchangeable.
Okay, I heard you. One person's saying it can be interchangeable. And I think, what?
I agree with Sally as well.
You agree with Sally?
Because the iron can affect the water, or the water can affect the iron.
And I would agree with that assessment. You can think of iron as being the system. You could think of water as being the system. Or you could think either one of them. It doesn't matter. Okay? Because what's happening is we're assuming this is a mini universe, perfectly insulated from the rest of our known real universe. Okay? And we're going to move energy from system and surroundings. The amount of energy doesn't change in the total universe, right? So it doesn't matter which one's the system or surroundings because we can only move it from one place to the other. Okay? Those are good questions. All right. So look, the total Q in the water, because the energy in the universe isn't going to change, and the energy in our little mini isolated universe isn't going to change, then the energy in the water is going to, the energy change, or the whatever amount of water change, energy change we have, is going to equal whatever energy is lost by the iron. The energy gained by the water has to equal the energy lost by the iron, because it's totally isolated, and we can't add to or take away energy from our little mini universe. Got it? All right, then. Whew. All right, if you look up this, we already know the specific heat for water. Okay, we already know the mass for the water and the iron. We need the specific heat for the iron. If I look up the specific heat for iron, I found it in one location as 449 joules. I'm sorry, kilojoule. No. Yeah, joules per degree C per kilogram. But I want it in grams because I'm measuring in grams. So I know that there are 1,000 grams in 1 kilogram. And so I use that to build a conversion unit, 1 kilogram and 1,000 grams. And I found that my specific heat for iron in grams is 0.449 joules per degree C per gram. Okay? So that's our specific heat for iron. Well, you wouldn't. I'd have to look it up or have to give it to you or something. Okay? All right. You also know change in temperature is always temperature final minus temperature initial. Okay? So the change in temperature is made of this equation, yes? All right, let's put these two equations together because whatever the change in energy of the water, it has to equal the inverse of the change in energy for the iron. All right? So let's plug these two equations in for this. So we've got the mass of water times the specific heat for the water times the change in temperature for the water. And that's going to equal the negative of mass of the iron times the specific heat for the iron times the change in temperature for the iron. Got it? All right. Remember, the final temperature is going to be the same for both when we get to the end. There's a point where it reaches equilibrium, and the final temperature is the same for both. Okay? So whether we're talking iron or water, final temperature is the same number. What we know right now is we know the initial temperature. The initial temperature for the water is 10 degrees. The initial temperature for the iron is 45 degrees, right? We don't know the final temperature. But let's plug this equation into this because what we don't know is we know the change in temperature. We know there is a change in temperature. What we're trying to find is the final temperature. Got it? All right. So we got the mass of water times the specific heat for the water times temperature final for water minus temperature initial for water. Okay? Now that equals the inverse of mass of the iron times specific heat for the iron times temperature final for the iron minus temperature initial for the iron. Okay? And since temperature final is the same for both when we get to the end of it, we really don't need to say temperature final for iron and water, because those are going to be the same number. Does that make sense? Now we can start plugging in numbers.
I have a question. So that first,
Okay. We're ready to start plugging in some values. So let's see, the mass of the water, 300 grams, yes? Specific heat for the water, 4.18 joules per degree C per gram. Temperature final for water we don't know, so we leave it to TF. We do know the initial temperature for the water is 10 degrees C. Alright? And that's equal to the inverse over here. Mass of the iron is 50.0 grams times the specific heat for the iron, 0.449 joules per degree C per gram, times temperature final we don't know, but it's the same for both iron and water, minus 45.0 degrees C. And what we have to solve for is temperature final. We only have one unknown. So we have some moving around to do. So let's sort of brainstorm about how we're going to solve this problem, okay? All right. When I have multiplication and addition and subtraction in the same part of the problem, what do you have to do to solve this? It's the distributive property. I think that's what it's called. I'm not a math teacher, but if I remember correctly, it's the distributive property. So it's this times this times this minus this times this times this. Does that make sense? Is that correct? All right, let's do that then on both sides. This times this times this minus this times this times this. Okay? And you work on it on your paper. I'll work on it up here, and we'll compare notes when we get to the end of that part of it and see how yours looks, how closely yours is aligned with mine. Okay? All right. Gonna need another minute to get yours collected. So this times this times this is this part right here. This times this times this is this part right here. And we subtracted. Then I isolated this whole thing over here, putting negative outside, okay, in both places. This times this times this is this part. The minus here is what I have here. This times this times this is what I have here. Okay, now by setting it up like this and collecting everything, I can cancel out some units of measurement. Okay? I've got grams at the top and grams at the bottom. I can cancel those because this is all multiplication now. Okay? In this stage, I can cancel grams. I can also cancel degrees C. And down here, I can do the same thing. Grams cancel here. And right here, grams, top and bottom cancel, degrees C, top and bottom cancel. Okay? So now let's collect up these parts. I want to do this math, and do this math, and do this math, and do this math, and sort of collect it all together a bit, okay? So you do that with me, and then we'll compare our answers when we get to the end of this process, all right? So this times this times this gives me this, minus, minus. This times this times this gives me that, equals, equals, negative, negative. This times this times this gives me this, minus, minus. This times this times this gives me this. I went ahead and applied the negative here to this whole side. So this negative times this positive gives me a negative number here. This negative times this negative gives me a positive here. Does that make sense to everybody so far? All right. That's actually the hardest part of the work here. The rest of it's just a little some more mathematical or algebraic manipulation. I want to get these terms on the same side of the equal sign and these terms on the same side of the equal sign. Okay? So if I want to get this one right here over on, I want to get both of these on say, the left side, then what I need to do is to add this term to both sides. Because this is a negative, if I add that term, it's going to cancel out this side, right? Okay, so let's do that first. Let's take this and add this term to both sides. So I'm going to do plus 22.45 joules times temperature final over degrees C, and I'm going to do the same thing over here. Add 22.45 joules times temperature final over degrees C. Okay. Now this side because this is a negative and this is a positive, everything else is the same, all this cancels out. Make sense? I want to move this term over to this side. So to do that, I'm going to add, since this is a negative, we're subtracting that one, I'm going to add it down here. So plus 12540 joules and plus 12540 joules over here. So this minus and plus, that whole thing cancels out over here. All right, I've collected terms here. All right, I've got all the terms the same on both sides. All I got to do is do the math now, where I add these and add these. All right, so we're keeping this part as part of this equal stuff up on this side. That makes sense to you? Any questions about that so far? All right then, if we add this and this together, I get 1276.45 joules times temperature final over degree C. Now I hope you're doing this for yourself in your own calculator to make sure, and you're doing all the math for yourself and then looking at what I'm doing rather than just copying down what I do. Copying down what I do is passive learning. Doing it for yourself and then comparing, that's active learning. Active learning is far more efficient and effective than passive learning. Okay? You have to do this 15 times to get it right if you're just doing passive learning, whereas you might only have to do it once or twice if you're doing active learning. Okay? Active learning is far more efficient than just passive learning. And everybody says, I learn by doing. Well, do it. Okay? All right. So here's our equal sign, and over here we're adding these two terms together. And we get 13550.3 joules over 1. Okay?
Why so much space in between?
Because I'm adding them vertically here just to keep them lined up. Just for now. It's not a big deal. I can put them close together if I wanted to. All right. Not far from being done here. Okay? What I want to do really in the end is get temperature final by itself. I'm doing all this to be able to isolate temperature final because that's what I'm looking for. Okay? Back up here, we're trying to find all this stuff. We said that the temperature would be the same at the end, and what we want to do is to find the final temperature. Okay? All right. If I want to get temperature final by itself on this side of the equation, what do I do mathematically to make that happen? Okay, so I need to, just this part here, I need to multiply all of this by the inverse of just this part. Okay, not the temperature final, but the inverse of all of this. Here's what he's saying. I'm going to put degree C over 1276.45 joules. Okay, if I do that, joules cancel, degree C cancels, and 1276.45 cancels. I've got temperature final by itself. But I can't do that to the left side unless I also do it to the right-hand side. So I've got to take this term and multiply this over here, degree C over 1276.45 joules. Okay? And what cancels over here? Just joules. What am I trying to find? Temperature. And I've got degree C. So this dimensional analysis process has left me with the units of measurement I'm looking for in the end. I just got to do this math. And that's a real simple math, isn't it? Therefore, temperature final is going to equal 10.6156 degrees C. Whew. But now look, well, that's a lot of math. These are not math skills that you don't already know. These are things you've learned. Some of these going back at least to 3rd grade. Okay? Distributive property, I don't know where that came in, but I know it was there by 5th grade. Okay? So you can do this stuff, but neatness counts. Handling your digits, which is what I've been teaching you from Unit 1 in dimensional analysis. We're now in Unit 10. Handling and canceling out units of measurement is really critical to getting this answer set up properly and solving it efficiently, okay? So I know when your 1st and 2nd grade teacher told you that neatness counts, you can't solve this unless you keep it neat. I dare you to try to be sloppy and solve this problem, okay? At least when you're beginning. All right? All right. Now, what I did not do, I did not try to handle significant digits at every step, which is what I've been teaching you all year. And that's for time. I wanted to get through the math without handling significant digits because the math seems kind of complex. All right? But the math processes are not complex. Each of these steps are simple, but it's complex because a lot of those little steps all added together, all put together in one big problem. Okay? That makes sense? All right. Now, so really the best way to handle significant digits anyway is to do all the math and go back through everything from the beginning and figure out significant digits at every step and then applying it to the final answer. Okay? If we did that, I think we're going to find out, and I'm not going to try to go through every step. You need to do that when you do this math, but I'm going to try to do it here. I think we're going to come out, if I've not missed anything, just looking at it quickly, I think we're going to come out with 3 significant digits when we get to the answer and final answer. Okay? So let's assume that to be correct and round this to be 3 significant digits. And we get a final answer then of 10.6 degrees C. Now, before we walk away from this, let's ask ourselves, is this reasonable? Before we started, we asked ourselves, where would we expect the temperatures to be when we get done? And the answer was, you expected the temperature to be somewhere between this temperature and this temperature, yes? We have that. It's in between. Barely. Okay, that's a good analysis there. That's a good observation. Barely. So let's see. Can we look at the math and figure out, should it be that close to the original temperature of the water? Why?
Because the iron is so much less. It's only 50 grams.
Okay. All right. One argument is because the mass of the iron is so much smaller. That makes sense. It'd be a lot closer to the temperature of the water if you got so much more water. Is that the only reason?
No, sir.
What?
The temperatures, the iron is the one.
Yeah, but I don't think where that temperature starts makes a huge difference. If I put 2 samples of water of the same mass together, I'd get a temperature that's perfectly in the middle, wouldn't I? Okay? But look at the specific heats. Water's approaching 10 times bigger. So you would expect that for that reason as well, the temperature would be closer to the original temperature for the water. So both these terms are much larger than both these terms. So this math works out, you would think, using the reasonableness test. I'm expecting my temperature to be much closer to the original temperature of water than for iron down here. Now, if I were doing this math because of what I know, you didn't know this until now. But what I know is, I would look at this math problem before I even started, and I would ask myself, where do I expect the temperature to end up being when I get to the end? I expect it to be in between, which is what you guys identified, and because these two terms are so much bigger than these two terms, I will expect the temperature to be much closer to the original temperature of water when I got done. That make sense?
Can we test this in here?
Can we test this in here? Certainly we could. Do we have time? No. What I have to do in this class is, because we are short on time we need for this unit, I'm truncating a bit this unit. We're not spending as much time on this unit. I would love to do a calorimetry lab with you where you could test this idea. Okay? but we just don't have time for it. Now look, the process is really simple. You can use styrofoam cups for this, because styrofoam cups are very good insulators. Okay, so our perfectly insulated container, styrofoam cups wouldn't be perfectly insulated, but they're pretty well insulated. So you could take a sample of water and put it in a styrofoam cup. If you want to be really good, put the styrofoam cup inside another styrofoam cup. Get a plastic lid, get a sample of iron, heat it up, find out what your original temperature of iron and water are, and your masses of both are. Put the iron in there, cover it, put a thermometer in there, and watch the temperature change. And when the temperature stops changing, see if your math doesn't work out.
It would take a long time to see like read stuff.
Would it take a long time? Probably not too long. It depends.
I guess since the water's so much more, it wouldn't take that long to rise.
Well, I would think within half an hour you should have a pretty good answer. Actually, if you had a really, really good thermometer, it would take longer than that, because the closer you get to the equilibrium temperature, the slower the change occurs, or seems to occur. Okay, the rate slows down. All right, and that makes sense too, I think.
Mm-hmm.
Yes. Yep. But we could do that, or you could do it at home. All right, but I think you kind of know what's supposed to happen. I have done this lab before, but we're just kind of where we can't really. Our lab for thermochemistry is ice cream.
I'll take that.
You'll take that? Good. And ice cream is, in many ways, the same thing. Let's remind ourselves of what an ice cream freezer looks like. How many of you ever made homemade ice cream? Okay, good. So you know what I'm talking about here. So in a homemade ice cream freezer, you've got a large container on the outside. And inside that larger container, you have a smaller container. Now, I've simplified it a bit because you've got a crank or a motor up here and other things like that. But your ice cream goes here. Okay?
Ice cream goes down.
The ice cream mix. It's liquid ice cream mix when you start.
Ice cream mix.
Okay? It'll become ice cream when it's frozen. All right?
I thought you put like real ice cream in. I'm like, that's not making ice cream by me.
No. All right. Then in the outside, you're going to put salt and water and ice, right?
Yeah.
And what's really doing the work is the salt water. Although there's some interaction between the ice as well.
Doesn't this like get it cold?
Actually, the funny thing is the ice doesn't get any colder. It's only the salt water that gets colder. But we'd have to go through a whole lot of explanation about the enthalpy involved in melting ice in a saltwater environment to understand. Okay? All right. We are going to simplify our calculations. This is a bit complex. Okay? We're going to assume that the container the ice cream is in doesn't affect the change at all. Now, we know that there's an effect, right? We're going to ignore that effect. Because really, if we were really good and doing really good calculations, we would figure out how much of an effect the container has in addition to the ice cream mix and everything else involved. We calculate the loss of energy to the surroundings. Because if you've ever made homemade ice cream, you know ice builds up on the outside. Okay, and so there's a loss of energy, or actually there's energy transfer. Energy is being transferred into it from the outside. We're going to assume that our ice cream freezer is perfectly insulated, which it can't be. All right? So we're going to simplify it down to the point where only energy is leaving the ice cream mix and going to the salt water ice mixture. Okay? Now, we're going to simplify it more than that, because we're going to assume the ice cream mix is already at the freezing temperature, but is still liquid. So going back over here to this chart, which is for water, but the pattern applies to any physical material, anything. We're going to assume that we've gotten the temperature down to the freezing temperature, but it has not started to freeze at all for our calculations and preparation for the lab. I'm simplifying to the point of absurdity here, guys. Okay? Got it? Because the calculation would be really complex without this simplification. Okay? For the salt water and ice mix, we're going to simplify that and say it's just salt water. Okay? And we've got this salt water down to as cold as we can get it without it freezing. And all we're going to look at is how much energy can be moved out of that salt water into the ice cream mix. That's how much we're going to simplify it. Okay? We're going to super simplify to the point of absurdity. Now look, because what we want to know, here's our question for the math. The math is not what is the final temperature like this math. The math for your ice cream prep is not what is the final temperature. Okay? Your math for this is similar to that. For this, we want to know is, can you freeze the ice cream given the conditions? That's our question. Not what is the final temperature, but can you freeze the ice cream given the conditions we're going to provide you. Now what I'm going to do is I want to email to you.
We got freeze ice cream, no?
What I'm going to do is I'm going to send to you by email a list of conditions. So everybody's going to have a different set of conditions. What you have to do is find your student ID number and find your conditions and do your math. Okay? So everybody's calculations are going to be different. You cannot just have somebody that's a little smarter than you give you their answer and copy it down. All right? You've got to do the math. All right.
So can you give us like a ballpark of what direction we're going to be going?
I'm giving you a ballpark right now. Just hold your horses. All right. All right. For the math prep, the first thing you want to know is how much energy needs to be removed from the ice cream to get it to freeze. We're going to make some assumptions. I want to make it simple for you. We're assuming the ice cream mix is at the freezing temperature but has not yet started to freeze. All you got to do is figure out how much energy has to be removed. Okay? So the ice cream mix will be in our calculations, it'll be at its freezing temperature. At its freezing temperature, but not frozen. In other words, it's liquid. Okay? Now, if I'm trying to freeze something, what does Q have to be?
Negative.
Negative. So you got to have a negative Q here, okay? Which means the delta H has to be
Negative.
negative. All right. Now the salt water, we're going to start out with saturated salt water in our calculations, in our super simplified to the point of absurdity calculations. Our salt water is saturated, that is to say it's got as much salt as we can get in there. At the lowest temperature I can get it before it starts to freeze. So that's at a negative 21 degrees C. Okay? Now, if the ice cream mix has to have negative Q to freeze, and the energy has to go to the salt water, what's the Q in the salt water have to be?
Positive.
Positive Q. Okay? The ice cream mix freezes at negative 13.0 degrees C. If you get any warmer than negative 13 degrees C, you can't freeze the ice cream. So don't tell me what the answer is, but I want you to tell me how do I figure out the temperature range for the salt water? We can't get any warmer than 13 degrees C or the ice cream mix won't freeze because that's its freezing temperature. The salt water is at negative 21. What's the temperature range?
20, 13, 13.
There you go. Between the two. Got it?
So,
All right.
Okay, so we do the math that we did now, and if I answer between those, then yes, it can be both.
All right. What we need here is a final temperature for the salt water that is less than or equal to a negative 13 degrees C. Essentially what you want to know is this. Is there enough positive Q over this temperature range? Is there enough positive Q available to satisfy the need to get rid of this amount of energy? That's your question. When you do the math, you're going to figure out this first. Okay? And then you're going to see if there's enough positive energy available here to freeze the ice cream. Okay? That's your goal. I'm going to send you the values that you're going to use. Everybody's going to have different values. Okay? And you're going to do the math. You use two different equations because this is one where we're changing state and this is one where we're changing temperature. We use those two equations in the homework from last night. Okay? But you're going to compare the Q you get here to the Q you want to get here. Is there enough available here to do this?
So we use the change in state for the
Yeah, because you have to. Change of state is one kind of equation, change in temperature is another. Okay? Now, you're going to do this math tonight. Listen carefully. You're going to do this math tonight. I will send you the spreadsheet that compares your student ID number against the values you're going to use. I'm going to give you a form, and you'll put your values into the form along with your answers. Okay? And then I will do my best to try and get all that evaluated before tomorrow. So you guys have a chance to revisit your math if it's not correct. Because you can't eat ice cream on Friday, 2 days from now, unless it is correct. I won't be here tomorrow. Okay? So what I'm going to do is I'm going to send you your notices by email. That's what I hope to do anyway, if I can get it all worked out.